Hi, my name is Matthew Shue, and I'll be presenting the Navier-Stokes equation. This talk is sponsored by Yoon Corporations and Yoon Talks PM. You might be wondering just what is the Navier-Stokes equation. So let's start by taking a look at these images. As you might have noticed, this is a picture of a waterfall, these are pictures of rapids, and this is a picture of an airplane. What might these pictures have in common? Well, that's kind of simple actually. They all have fluids in them. These two pictures might be obvious because, well, they have water in them, and that's obviously a fluid. But you might be asking, where's the fluid in this one? Well, it's actually everywhere. When I'm talking about fluid, I'm referring to any gas or any liquid. And this includes air, which is actually all around us right now.
The Navier-Stokes equation models the flow of fluids, and this includes naturally water as well as air.
Well, this is the Navier-Stokes equation. As you can see, it looks quite complicated. But let's break this down. Rho, which kind of looks like a P, stands for density. And this is the velocity field. This, as we have learned, is just partial derivatives. And this P, not rho, which might be kind of confusing, stands for pressure. This T stands for stress. And this F stands for body forces. This dot product, this is just a dot product of velocities, velocity vectors, as we've learned in the past. The equation kind of looks complicated. Well, that's because it really is. When you imagine the water, do you see all these ripples and like waves and all these weird movements per se? All of this has to be modeled by the Navier-Stokes equation. So obviously the equation itself has to be quite complicated. The equation itself is derived from basic physics. First, Newton's second law of motion is applied to relate the movement of a fluid particle to the forces that act on it. The main force is elastic stress, which is constituted by frictional forces caused by the viscosity of the fluid and the effects of pressure. However, like all traditional equations of classical mathematical physics, it is a continuum model, and this means that it has one fatal flaw. It assumes that fluids are infinitely divisible. And this is to say that the Navier-Stokes equation only loses touch with reality once you involve scales of infinitesimally small objects. So say, for example, molecules. And these small scale molecules are only important in the context of turbulence. So what is turbulence? Well, if you think about it, when you turn on a faucet, if you turn it on just a little, you'll get droplets of water coming out, say something like this. But if you turn it on to max, you'll get something like a frothy white substance, kind of like this. And this white substance you would also see in like the rapids of a river. And this is basically the effects of turbulence. You also might know turbulence as this, a bumpy air ride in an airplane. This is also the effects of turbulence. You might be wondering how you solve the Navier-Stokes equation. Well, honestly, it's really hard. Even Euler, who, well, back in the day was considered obviously a genius, could not actually solve it without making oversimplified assumptions. See, Euler was actually the first to make a model of the flow of fluids, but he made some really basic assumptions that helped him with his calculations. Euler assumed that fluids were incompressible and all fluids had no viscosity. And while these fluids made his calculations possible, they were really not in touch with reality at all. It wasn't until Claude Louis Navier and George Gabriel Stokes derived a system of partial derivation for the flow of viscous fluids in 1822 that this equation ultimately emerged. As you might have guessed, this is where the name of the equation comes from. Nonetheless, until recently, with the invention of supercomputers and wind tunnels, it was quite impossible for the Navier-Stokes equation to be solved. Instead, they modeled it. And perhaps this is, let's see, this is a model. It's often in the shape of a wind tunnel. And as you can see, it's basically just a small airplane inside a wind tunnel, hence the name. Well, in fact, there actually isn't a mathematical guarantee that the solutions of the Navier-Stokes equations always exist, or that if they do exist, that they are smooth. But if you do find a solution, make sure to email Yoon at flboe.com for a chance to win $1 million. The Navier-Stokes equation is nonetheless useful in modeling various fluids, even with turbulent flow. And this is because, as you can imagine, molecules are really, really small. And to account for the possibility of turbulence, mathematicians, rather than calculating on a really, really small scale, use statistical models for turbulence. The greatest application of the Navier-Stokes equation is certainly in transport. It's made air travel possible. And do you remember the middle school explanation for why airplanes stay afloat? It goes something like, airplane wings are shaped to move air faster over the top of the wings. When the air moves faster, the pressure of the air decreases. So the pressure on the top of the wing is less than the pressure on the bottom of the wing. And this difference in pressure creates a force on the wings that lifts the wing up into the air. And while this explanation is true, it's kind of just a gross understatement of why airplanes stay of the Navier-Stokes equation, which is really why the airplanes stay afloat. Back when airplanes were first invented, sure, the simple explanation was possible, but now in modern day, in order to keep a plane afloat with hundreds and hundreds of people, you would naturally want to make sure that every possibility has been calculated out, and that's what the Navier-Stokes equation has done. And in order to keep, obviously, because these calculations are so difficult, mathematicians themselves aren't the ones who calculate it, it's their supercomputers. Some further applications of the Navier-Stokes equation can be seen in the modeling of cars. And this is for more aerodynamically efficient cars. And this creates cars who have more mileage to fuel consumption ratios. And the modeling of water for ships is kind of similar, like the consumption of less fossil fuels for more mileage. And furthermore, it's also modeled blood flow in humans, as well as modeling carbon dioxide and methane for climate control. The use of that Navier-Stokes equation for modeling cars is that engineers can not only create more efficient cars, but also reduce their air drag. And this makes cars look both more sleek and cool, at the same time makes them more efficient. Modeling of blood flow in humans is useful for preventing heart malfunction. And for example, the modeling of blood flow has helped engineers develop medical devices called stents. These are tubes that keep the arteries open, and this helps prevent heart failure. Finally, the modeling of global warming, the changes of temperature on a large scale for purposes of climate change, individual small weather changes. For example, climate change would be considered like, today it's really hot, but yet tomorrow it's really cold. Even though on a large scale, the balance has not been changed too much. The climate, which is like today is sunny, but tomorrow it's really cold, has been changed drastically. These models, this can be modeled as well by the Navier-Stokes equation. Even though the two biggest aspects of modeling climates are the atmosphere and the oceans. Well, since the Navier-Stokes equation can be used to model both of them, the Navier-Stokes equation can see that our current situation in global warming. Although ultimately the Navier-Stokes equation can only speculate on what's going to happen and not prevent what's actually going to happen. Overall, the Navier-Stokes equation is quite useful. As you can imagine, everything in this world revolves around fluids. The air we're breathing right now is completely modeled by fluids, as well as the water you're going to drink, maybe the milk you're going to drink during lunch, and even the cars that you're going to drive will have some relevance to the Navier-Stokes equation. Even President Obama noted the importance of the Navier-Stokes equation, as indicated by this picture. This concludes my presentation for the Navier-Stokes equation. Thank you for listening. If you have any questions, make sure to email Yoon at jyoon@flboe.com. Thanks.